Challenge requirements and solutions.
Hello, I'm Nathan Heinger. I'm a programmer. I've been a part of the Technic's robotics team for 5 years. The first and most significant need of any robot is movement around the field to complete each of the tasks. Technic robotics team traditionally uses a 4-wheel drive base.
Hello, I am Alex Cook, and this is my 5th year on the Technic robotics team. I am the team captain and head designer for the team. We have been tasked to complete the assembly of the field robot. We need to transport 4 wheels, 1 arm, and a robot battery from the spotter's box across the field and place each part onto the field robot.
Hi, I am Alex Frazier. This is my 3rd year as a part of the Technic robotics team. One of the challenges for our robots to complete this season is to move the order boxes from their start position to desired locations around the field.
Hello, I am Caroline Govia, and this is my 2nd year on the Technic robotics team. I am a CAD designer for Technic, and I build parts and assemble the robot. Technic was challenged to create a robot that could move levers on the control box.
If any game pieces are dropped during a round, we have the option to collect those game pieces for a small point boost.
Optional challenges and solutions.
An arm for the field robot was provided for our team if we wished to use it. We also had the option to design a custom arm for the field robot. We chose to design a custom arm.
This year's challenge allows our team to program the control box or create a custom program that can be sent to the control box using an IR sensor. We chose to create our own program. Functionality.
The Quadica is an attachment that has several functions. It cradles all 4 of the field robot wheels on a thin piece of duct tape. The magnets on the field robot and the wheels easily connect through the duct tape, allowing for them to be installed onto the field robot while the robot moves away. The Quadica also cradles and carries the custom arm and attaches it onto the field robot.
The robot's arm has a cross member. When the arm is lowered inside the order boxes, it fits inside the top rim of the box and pulls the order box snug to the front of the robot. This allows the robot to drive while holding tight to the order boxes and place them in designated locations on the field.
Our programming uses the IR sensor to send commands to the control box, allowing us to change the functionality of the control box in roughly 1 second. By using this program, our robot can switch the movements and the speeds of the robot with the push of 1 button.
The sidearm moves in and out, which allows it to move 1 control box lever at a time.
Here's the block diagram. Our robot only uses motors. The 2 large motors each attached to a gear. The gear connects to another gear on the back of each wheel. This powers our 4-wheel drive. One of our small motors powers a small gear, which is attached to a rack and pinion that moves our sidearm out and in. Our other small motor is attached to a gear that turns and connects with a much larger gear on the arm, enabling it to move up and down.
Prototyping.
Originally, I designed the Quadica to be an attachment on the robot that could transport the field robot's wheels onto the field robot. However, it became apparent that the Quadica could both be used as a main function of the bot and to transport most, if not all, of the field robot's parts to the field robot.
I came up with the idea of the wheel box as a way to hold the magnetic wheels we need to place on the field robot. It was supposed to work in conjunction with a servo gripper arm so that we could hold all 4 wheels at once and subsequently load them into their places using the arm. It also included hooks on the exterior to hold the battery box.
These 2 pieces of wood on the collector would start in a folded position on the team bot to preserve our length requirement. Once the round began, they would pop out using a servo and remain out for the rest of the round. These would allow us to push the boxes while also carrying the wheels and the battery box on the wheel box and the field arm in our C-claw.
These forks were designed to be placed in the back of the robot, allowing the robot to move order boxes. The idea is that they could go into the PVC pipes at the bottom of the boxes, which was unrealistic due to the amount of accuracy required while driving.
This jointed arm and claw was designed to use a servo to pick up the field robot's arm and battery box and move the levers by grabbing the top of the lever and pulling it back and forth. The weaknesses of this design were its inability to place the wheels on the field robot and its lack of precision when moving the levers back and forth.
The sidearm was designed to mount on the tower and move back and forth so it could quickly change between levers to save time. It also has a hook to easily grab the stem of the levers in order to move them. This is the first of several custom arms for the field robot.
Technical solutions.
We decided the size of our wheels and the size of the gears that are used to power the wheels by calculating gear ratio. The large motor connects to a large gear, and the large gear meshes with a small gear on the inside of each wheel.
The arm moves with a single gear reduction 4-bar linkage. The small motor is attached to the large arm and mini gear. That gear travels up and down on a large gear that is mounted to the robot tower.
Because the Quadica was designed to utilize the strength of the neodymium magnets on both the wheels and the field robot, no motors or servos are necessary for the release of the wheels from the Quadica.
We designed the bot to be able to control one of the levers on the field control box. It is faster to use the IR sensor to change the function of one lever and change the speed of said function than it would be to move the robot's sidearm to a different control box lever.
The sidearm is mounted on a rack and pinion and is powered by a small motor.
Design specifications.
The weight of the robot is 16.5 pounds. The robot is 8.5 inches wide, 10.75 inches long, and 17.5 inches tall. The speed of the robot is 28 inches per second. The robot is capable of lifting 12 pounds. The structural integrity of the robot is robust. The robot is powered by a 7.2 V3000 mAh. The processor used for the robot is a ST Microelectronic ARMS Cortex M3. The robot is 90% accurate.
We have used a 4-wheel drive system in previous years and thought it gave us the best chance to remain small, fast, and maneuverable. We quickly settled on 5-inch wheels, the same size as last year. Our arm has a 4-bar linkage, which would allow the Quadica to move up and down while staying parallel to the floor, which prohibits the pieces it is carrying from falling and makes it more maneuverable while placing the wheels, arm, and battery on the squeaky. To power the arm, we decided to use the same single gear reduction as last year. We fixed the gear to the tower and added the motor to the rear of the arm. This allows the motor to act as a counterweight.
The bot is powered by a VEX battery, which is plugged into the motor cortex. The motor cortex is programmed to control 2 large motors, 2 small motors, and 4 servos, which are provided in the returnables kit for Best Robotics. We are currently only using 4 motors and no servos for the made-to-order season. We program our robot using Simulink, which is a programming language created by MATLAB.
We tested our robot for the first time at Mall Day. First, we tested our IR sensor and made adjustments to the programming so that it would function correctly. We tested the Quadica and discovered that our field wheels were too small, and in turn, the Quadica brackets were too thick. We removed a few layers of duct tape to adjust for this issue.
Innovative design elements.
At first, the Quadica was only meant to be able to transport the wheels of the field robot. However, after we decided it would become the main function of the robot as an attachment to the arm, we discovered ways to maximize the efficiency of the Quadica. One addition was to add hooks to carry the field robot arm. Another was extending the length of the outer brackets to allow for the field robot arm to be placed on the field robot.
Sam Linhart designed the sidearm. This arm moves back and forth using a rack and pinion and does not need any independent moving parts. Because it is attached to the side of the robot, it can be precisely aligned with the control box, allowing the IR sensor to work while the sidearm is moving. This allows the driver to alter the program and continue moving the field robot while only the pause for 1 second to send each command is needed.
Royal Technic has built one robot that had a 2-wheel drive base. That robot was used during the Bet the Farm year. Since then, Royal Technic has built 4-wheel drive robots. We do so because the 4-wheel drive design allows us to have extra speed, spin in place, and have extra power. Lessons learned. This is my 3rd year on the robotics team, and I learned that the design that you think you're going to be using for the task doesn't always work out, and you often end up creating an even better design.
This is my 2nd year in robotics, but my 1st year working with wood and building a largely wooden robot. Having been used to cutting and drilling metal for BattleBots last year, I found that wood is a lot easier to work with. Also, I've never gone through the entire engineering design process before. I really enjoyed learning how to draw my ideas and build models to better evaluate the feasibility of different options for our robot.
This is my 5th year in robotics, and I have learned that even though I've acquired a lot of programming and wiring experience throughout the years, I still need to have patience this year, as the control box and squeaky have been very difficult for me to wire and to program.
This is my 5th year on the robotics team, and I'm always amazed at what I learn, even when I think I know how to do something well. This year, that lesson revolved around having 3 new drivers. When designing a robot, I am inclined to make certain components more optimal, but they have often required seasoned driving techniques. For me, these challenges seemed easy enough, but when thinking of 3 brand new drivers, components needed to be designed with larger margin for error.